We start the session, sir.
All right. Thank you very much.
Yeah, okay. I'll just give an introduction and then hand over to you, sir.
Right.
Thanks. Oh, okay. Good morning to
Good
all of
morning.
you. Good evening and good afternoon for participants joining from different geographies. Okay, we will start the parallel session, second day today. So for this session, I would like to introduce our chair and co-chair. Engineer Ravi Sundaram will be chairing this session. Engineer Ravi Sundaram is a postgraduate in Geotechnical Engineering from IIT Delhi. He has over 40 years of experience in site investigations, pile foundations, and ground improvement. His international experience include offshore soil investigation and offshore driven piles. He started his career with McClelland International USA and worked on the company's projects in Saudi Arabia and Qatar. He has published over 65 technical papers that reflect his experience in geotechnical engineering practice. He was chairman IGS Delhi chapter during the period 2009 to 11 and is currently the executive committee member of Indian Geotechnical Society. On behalf of the organizing committee, a warm welcome to you, sir.
Thank you very much. Thank you.
We also have Dr. Rajiv Sarkar as the co-chair of the session. Dr. Rajiv Sarkar is an assistant professor in the engineering department at IIT ISM Dhanbad. He's obtained his PhD from Indian Institute of Technology, Roorkee, in 2009. Dr. Sarkar's area of interest includes soil structure interaction, liquefaction of soils, ground improvement, and discrete element method. He has published more than 30 research papers in reputed international, national journals and conferences. Welcome you, Dr. Rajiv Sarkar, on behalf of the organizing committee as a co-chair
Thank you
for
very
this
much.
session.
Thank you.
So with this, I will hand over the session to chair and co-chair to manage further. Over to you, sir.
Thank you very much, Dr. Parthasarthi. It's a great opportunity to participate in this international conference and also be the chair for this technical session. Without taking much of your time, I will invite Dr. Ashish Juneja to make his presentation. It's really a great honor for us that Dr. Juneja from IIT Bombay is going to be talking on disturbance in soil structure interaction due to post-cyclic recompression. Now I hand over the session to the co-chairman, Dr. Rajiv, for his initial remarks, and then Dr. Ashish can start his presentation.
Okay, let me start with the Professor Juneja's brief bio. That Professor Juneja is a professor in the Department of Civil Engineering at IIT Bombay from 2005. He has more than 70 publications with over 300 citations from various national and international journals and conferences. He received his PhD in Geotechnical Engineering in the year 2002 from National University of Singapore, Singapore. He has twice received the Excellence in Teaching Award in the year 2012 and 2016, besides Best Paper Awards by IGS and other geotechnical agencies. Professor Juneja has served as a consultant to agencies such as Indian Railways, NHSRCL, NPCIL, Mumbai Metro and Nagpur Metro, BMC, Samsung Engineering, John De Null and John Deere. The project for Konkan Railways resulted in him being awarded the 2014 IIT Bombay Industrial Impact Award. With this, I like to hand over the session to Professor Juneja for the presentation of his special lecture on disturbance in soil structure due to post-cyclic recompression. Thank you, sir. Over to you, sir.
Yeah, thank you, Professor Sarkar. It is indeed an honor to be invited in this prestigious conference, and And to be honest, it seems the way it has been planned and the way the background images appear as if we are in the conference venue. And if you happen to zoom in, you can actually take the first row seat, which, right in the first row seat of the conference hall. Okay, with this, I like to, spend the next 15 to 20 minutes to just to tell what we have recently, done something in our laboratory and, examine what really, what happens to soil after they are subjected to numerous cycles of loading. The genesis of this, in fact, comes from the figure on the right-hand side. What you see is the railway embankment. Some of you may recall that quite a few years back, the then railway, the honorable railway minister had overnight increased the axle load of the, the train, the track, the load on the railway tracks. If I remember, I think from 20-21 ton, it was jumped to right to 25 ton or so, maybe more. But you can pull out those figures. But this tremendous jump, overnight jump, was done without giving a scientific thought to it. And lo, all the embankments they perform successfully. So in a way, there has to be a certain background to it, that the soils which have been subjected to cyclic loads from the railways. So as an example, you see the high frequency loads which have come from the railway track, the wagons and the engine, especially the engine as well. So these have, because of this subjection to these loads, the soils below have over the period, undergone deformation. As a result, their bearing capacity or the strength have improved. So we are looking at what soils, the improvement, and at least to quantify those numbers. So this is a work by Dr. Muhammad during his PhD. Aslam, he's now he's very well established, and I'm grateful. So all these slides which are present are in fact from his PhD work. Okay, so to give you a brief background, what really we mean by when the soils are subjected and what happens. If you look at an ordinary triaxial test, the figure on the left hand side shows the same sample. I mean, the same soil with the same void ratio, but one is subjected to a higher, confining stress. The other one is subjected to lower confining stress. So lower confining stress, common sense tells us it'll show us a hump and a drop. A higher confining stress will be more like irrespective it's clay or sand, it'll show you like a normally consolidated soil, something like that. So to understand these two figures, look at the compression space which is on your right hand side. Both A and B have similar void ratio, but because they lie on either side of the ultimate line or the critical state line, you see that the sample A or the soil A will compress and soil B will dilate. Now it means it's important to understand that the soil from these curves is not only nonlinear, plastic, but is also stress dependent. This stress dependency is something which we like to examine in the next 10-15 minutes. Now, if you look at an ordinary Moore Coulomb or even those Cam Clay kind of models, what you see is look at this E log P curve, your standard E log P curve. What you see is, if I'm on the URL unloading reloading line, can I just make this mouse thing as a, just a second, please. I'm just trying to make this as a pointer. Okay.
Right click, yeah. Thanks.
So if you look at the unloading reloading line, so both Moore Coulomb or those Cam Clay family of models, they'll tell you, no matter you go millions of times on this line, you'll just retrace this every time, you'll retrace this path. So the same thing happens when you do multiple, loading, unloading. So it's just a replicate of that figure. The same, and if you look at the stress space, starting from A, going up to B, and if I unload D to B and then reload it, like my, any kind of dynamic load I apply, it just goes up and down with no change in any additional strains occurring, and no new development of shear volumetric strains being developed. Okay. However, what you see is if I have multiple load cycles which are going at a certain period of time, what you see is the core pressure development in the first cycle, and then in the second cycle and third cycle, it's not the same each time. You do see a different response which is more like a real life scenario. So the bottom line is you do need a kind of something like a slightly more sophisticated soil model to understand this phenomena which occurs. And of course, I'd like to just give a brief background on what happens to soil during loading. During loading, majority of you would be knowing you can either have a flow type failure, meaning loose sand or normally consolidated soil. They're quite nice up to a certain number of sites, and then bang, it fails. Dense deposits will have more like cyclic, wherein the mobility, wherein the deformation increases, and this would first and second case are more serious. The third one is where if you have, for example, the soil is still trying to accumulate a lot of plastic strains, and it does not really reach its ultimate state. It just continues to take in more load. So we'll concentrate, in fact, more on first and the second type, because if you look at it, these are the soils which are really studied for liquefaction studies. And also we look at the third one, because these are the ones which actually interest us for long-term stability of embankment, which is the case here. So the contents of my next 15 minutes are going to be, I'm going to present something on what are the stress core pressure changes in soil when the soil is subjected to a lot of cycle loads. Try to present some degradation model similar to your structured soil model. So very simple model. Of course, there are quite complex models, but as we understand, because of the limited data available, a lot of those recent models which have been developed, it's really very hard to comprehend because of the number of input parameters. And also speak about what happens in the post drainage, whether it's intermediate or post drainage. And briefly, if we get time, to comment on this observed changes in soil structure. So we have three kind of soil samples which we used. One is two are the sands. That's the first and the last column. What you see is the sands are the first sand is more like rounded. It's like rounded particles, and the last one is more like angular particles. We also use silt size particle, which is way more like subangular to angular. So, and all these soils were shown to lie within the potentially liquefiable, deposits. The routine lab tests were done, so this is pretty much routine. One additional thing which I like to highlight over here is the kind of sample preparation method. So sands are normally, either prepared by, pluvator. That's the preferred method for us. So I like to speak about pluvator. Although for silty deposits, I think we went on for under compaction method, which which is routinely followed. But I like to look at the pluvator which we have in our laboratory, and which we try to model using DEM. So that's a simple a single soil particle. If you look at it, maybe at 1 second it's somewhere here. And it falls down and then rebounds. But I like you to look at the graph which is on the left. So at 1 second, it's still somewhere, it's not moving. That's 1 second, it's still there. At 1.5 seconds, that's the vertical line, it starts to drop. So 1.5 seconds, it drops. At about 1.78 seconds, it hits the perforated plate. So that's the first break happens. It's just like a break, it breaks the energy. So that's where the first 1.78 seconds you see is some kind of elastic rebound happening. And then thereafter at 2.1 seconds or so, it drops to the inside the container, and wherein its velocity all of a sudden becomes not zero, but because of this energetic layer, there is some up and down rebound of the particle which happens. Now this energetic layer controls your quality of your sample. Okay, there's been a lot of work done, and we are also trying to give a little bit input to it. What you see is the energetic layer plays an important role, at least in the quality of the sample. Please look at the small figure, if you can see at the bottom, and I hope you have the front row seat by zooming in onto the PPT presentation. What you see is, the sample quality which has more like a variable height diffuser. This is what we normally would like to advise. The diffuser should be able to go up, move up as the particles get filled up in the container. Obviously, because you want the constant height of fall, but you're fixing the first perforated plate, or the first plate which actually helps break the larger size, I won't say lumps, because this is all granular particle, but it does not allow the soil to fall in lumpy kind of manner. So the other one, which is more like static, you see there is difference in the void ratio. So these small values, of course, will play whenever we need to explain some kind of background. These do help in understanding that why my soil has behaved in such a way. But having said that, what you see is the ultimate state. That means the friction angle at its ultimate state. That's the first figure. Irrespective of what kind of sample preparation method you have used, or the figure on the right, which shows other critical state parameters from compression space, it means that the constant volume failure, or the failure at, which happens at ultimate state, those conditions do not change irrespective of what kind of sample preparation method you use. But having said that, there is, for dynamic loading, there is a substantial difference. If you compare the figures on the left and right, the moist time sample, if you really take a hand lens and look at them carefully, they give you less number of cycles to reach liquefaction compared to the pluviated samples. Pluviated samples are about, if you look at those numbers, they are a bit, but notably higher. So this, in fact, we always say pluviated samples replicate more of a natural kind of deposit. So these are typical, cyclic loading curves, and let's not go into that. It's typical standard. One additional thing is what we noticed was the excess pore pressure ratio when we plot against the number of cycles. So if I take one single test in something like 1,000 cycle or maybe 10,000 cycles, a blue line shows a single test going straight away, and the grayish kind of line shows the same, similar sample, soil sample, but this time it undergoes in thousands, in this case, hundreds of cycles. The right side is thousands of cycles. And after each 1,000 cycle or so, it's allowed to drain and then start the undrained loading again. Obviously, this excess pore pressure ratio on the vertical axis does not do justice to it, because it doesn't show a drop and the drop. But we have broken down each and every channel of the 10 cyclic loading, 10 sets of cyclic loading, and then added them up. So again, excuse me, the vertical axis, it probably should not be compared to those figures on the left hand side. But what we see is the triaxial test results, irrespective of whether we went stepwise or one single go of maybe 10,000 cycles or more, the test results seem to suggest that the stress strain response is quite similar. So this led us to the very basic the degradation parameter, the development. Which is really, I think it's more than for 30 years old. I think Ni et al, they have used it probably a couple of decades back, and A number of, so that's a degradation parameter similar to for your structured clay. What it's seen is that if I introduce this, can I just develop or use this degradation parameter in terms of, I think this is Z times eta, so that's Z. Probably what you see is, yes, if I plot the number of cycles to failure and try to get a relationship between the degradation parameter, I do get some kind of very obvious relationship. Even the figure on the right hand side will help us that this is cyclic stress, but I can also use, it's a CSR, so I can, because all the samples in this case were tested to I think the starting confining pressure were quite similar, I think 100 kP or so. So what you see is you can develop some relationship, and let's see with this relationship, are we able to, curve fit it? So that's what engineers are happy with it. What you see is with very large number of cycles, maybe about 100,000 or so, you cannot, there is large difference. Although with less cycles of up to 100, it gets a good really fit. Obviously, because you're trying to combine connect the two ends of the curve, like it's not the whole curve, so two ends are being connected. But for majority of the tests wherein the number of cycles are large, it's difficult to connect. So even over here, what you see is so this degradation parameter is not helpful. There are other models, power model, which have to curve fit parameters A and B, and you can do this. So idea is you trace, how do you trace this pore pressure ratio, excess pore pressure ratio against N. But again, this has limitation because you still are not able to connect. So we can. There are hyperbolic models again with two unknowns, and with the development of more curve fitting platforms. As student or we can sit down and get endless fits, but none of them give any theoretical background to what really happens. So in last couple of decades, you will see a lot of papers which have come out, but there's no theoretical background. Of course, they use a lot of less computation. They come at a lot less computational cost, and they are simple. What we would like to see is something wherein you can, at least the soil performance can tell us, it is not only the pore pressure response, but also whether we can see whether the strains and stresses, they also are able to, tell us something more about the performance of the soil. So that figure on the top left is something which tells us how the model we have just said it can go up and down. But now in this case, what we have done is that's what do you call it? Stable boundary surface which is shown. And if I start the soil loading from a point A over here, after when the unloading starts, it reaches another value of it reaches another elastic leaf of A2. So somewhere it starts to load and it's still inside the it reaches the elastic leaf which is still inside. So if we can somehow adjust the hardening parameter, which is given by this line over here, NCL. So some of you may be familiar with hardening parameter like P0 prime, and we bring in some kind of again a degradation theta as we have brought in, but this time we are trying to adjust the hardening parameter in such a way that it reduces the size of the yield surface each time you do a cyclic loading. So somehow my new P prime value or P0 prime value is less than the starting. So let me say if this figure, if I have this over here, and after loading, it starts to understand a new P0 prime. And with this new P0 prime, if I load it, it will go to a different set of, again, it'll start to give me a different performance in terms of pore pressure response, in terms of effective mean stress, etc. So these equations on the right are not there to scare you. I apologize, but if some of you understand that elastic, these are your Hooke's law relationship, but the plastic strains which we use are typically from, these are associated flow rules. And I mean, the idea is to look at whether we can have a degradation parameter this time, which can adjust the pre-consolidation pressure. So this is what we have done.
Sorry to interrupt, sir. Sir, it is almost 15 to 20 minutes is over.
I'll just take another 2 minutes if it's all right.
Okay, sir.
Okay, thank you. So this degradation parameter, as we said, it's like it varies from 0 to 1. 0 would mean your typical Moore Coulomb or Campley, and 1 would mean that your hardening parameter is made to change. So I'll just skip through some of the additional slides. I'm sorry, it's just I think. Let me go to the next one. I'll go to directly to what is the final one. So apologize. Yes. So the final one is with the adjustment against the number of the hardening parameter, we are able to model the response of the soil with only 2 additional unknowns. 2 additional unknowns, and this is the beauty of this simple model. I'll skip this. Yes. So after the the cyclic loading is over, we are looking at what is the volumetric strain in the sample against the pore pressure response. So the volumetric strain is your change in void ratio over 1 plus void ratio. That's the horizontal axis. What you see is with samples which have high pore pressure ratio and less pore pressure ratio, you can still string the data along a single line. But it's interesting to see what really happens to these. This is probably the last thing which I like to highlight in this is with samples which have RU less than 0.75. So you can take it as a magic number, but what you see is the unloading reloading line, which is shown by black arrows over here. It doesn't make much of a difference. The property of the URL or the kappa, as we say, is the same. But with RU more than 0.75, what we see is there is a change in the slope of the unloading reloading line, meaning the structure of the soil is changed when your pore pressure response is high. And in fact, these numbers can, just to give you some, these numbers can vary anything from 2 to 4. So your gradient of your unloading reloading line is large. I'll again. Yeah, this is, so again with this background, can we now predict what is the increase in strength? So Q star is your new strength divided by old strength. So that's undrained deviatoric strength increase divided by the old one. And that's your OCR. So that's OCR by definition. So if you look at the paper, the definition of OCR is slightly defined over there, how OCR we have taken. But are you less than 0.75, you still see that the performance of the silty or the angular sample is better compared to the rounded granular deposits. And if I have RU more than 0.75, that is when the sample really the pore pressure response is higher. What we see is the increase in strength, okay, is kind of seems to be independent of your CSR. That's again an interesting thing, but again, it has a relationship between OCR over here and the power which we have OCR to the power of some kind of capital lambda over here, capital lambda over here. This capital lambda, our work has shown, can be obtained even from your standard triaxial test. Meaning, if I need to find the strength of the soil, the increase in strength of the soil due to dynamic loading, I really do not need any cyclic triaxial test. I do my routine triaxial testing, that is my drained and undrained triaxial, get my capital lambda from there, and I can see I can predict what is my increase in strength. And in this case, it shows the increase in stiffness.
Dr. Juneja, may I request you? Yeah, okay.
Yeah, with this, I'll just conclude the presentation that the post-cyclic characteristics of the soil are dependent on the pore pressure accumulation function, which is again based on numerous work. You can work over it. And of course, we have given some hint on the particle size and shape, which makes some effect on the performance on the response. Okay, with this, I'm sorry I took additional, I think, 5 minutes. I'm really grateful to the chairman and vice chairman for, allowing me to speak. Thank you.
Dr. Juneja, it was a very interesting presentation. That is what prompted me to, give you as much time to speak. I wish we had the opportunity of listening to you some more, but definitely I think there will be in the future. Thank you very much for your very vivid presentation. Now I request Dr. Rajiv Sarkar to, ask for the questions, and then we can move further.
I can wait up to the end for the questions if you want. I'll stay up to the end of the session.
No problem. If I had one small question.
Please.
Have you been able to apply these principles on any specific project sites to see how, actually what happens after liquefaction, the post-earthquake response, or something like that?
No, not yet.
Okay,
but we have only seen non-liquefiable soils. We have more like concentrated on those kind of thing which we have not reached liquefaction stage, because I think more like data is very limited for liquefied soils. So we were more onto the performance of soils which are just under routine machine foundation loads or railway loads.
So you have applied these on such kind of applications in the field, is it?
No, not in the field.
Maybe in the laboratory some tests have been done?
We have only done some numerical studies, simulations. That is the limitation.
So I think there is a lot of potential for, application and, to real life situations. I look forward to, seeing more research from you on this subject, because this is something which is really of very great interest. What happens after liquefaction? People only talk about whether the soil will liquefy or not liquefy, and then if it is not going to liquefy, everybody thinks it's a very happy situation, and you move ahead.
Agreed.
Before I conclude, then I'd like to invite Dr. Ashish Juneja, if you have any remarks.
This is, I want for you a remark regarding the conclusion of the session.
Yeah, regarding the papers presented.
Yes.
And anything which you would like to add on your own presentation?
I actually...
Just because we have the time, so I thought we can utilize it effectively.
Yes, very correct. So the thing is, I really like what Chairman has asked, because the practical implication of all the presentations today is something pretty important, and we should focus on that when we start to do any kind of experimental or theoretical work. And given the level of expertise in the different, the experiments and the numerical simulations which have been, presented today, I feel that, we have done pretty well, at least in terms of the, the knowledge, or in terms of the equipment, in terms of the expertise of all the presenters today. So I enjoyed all the presentations, all the 3 presentations which I, saw them today. I think there were 3. And to be this, the presentation by Adhyasha is in fact known because I am her RPC member, Research Progress Committee member.
Okay.
So I was glad that to really hear her and see her. The other presentations were very nice. So I'm only now regretting that if I had those 5 extra minutes or 3 extra minutes at the beginning, I would have also done justice to what I wanted to say.
I appreciate what you're saying and apologize. I hope that we will get further opportunities to listen
Yes,
to you.
definitely.
Actually, myself, I being a practical field person, I always try to look for how these can be applied in the field. And that's what excites me. So, in fact, even whatever questions I asked were all related to how can I go and put this on the ground. That is the main thrust, which I feel academia, industry, if that energy transfer is there, I don't know about technology transfer, then there will be a lot of real life problems going to the research and research being applied in the field. I think that's how we should move ahead. I think then geotechnical engineering, we would have done justice to it.
This is very, very true, because I think what we should also be looking at is also on the same lines as having a kind of a steering committee. So when the research aspects of any research project is developed, along with the progress committee members, which are again from the academia, we should have members from the industry as part of the steering committee, because they are the real people who actually know whether this such a project, how far its implementation will be possible in the field. Because we they and to a larger scale, I mean, of course, when I say implementation means extend the whole thing to a bigger and larger scale. So I very much appreciate and like this, and maybe in the very near future, whenever we have a research progress committee coming up, I would definitely recommend that members from the at least one or two member from the industry, experienced member, they should be part of the steering committee.
That would be very good.
Mhm.
Dr. Partha, you have anything to add?
Yeah, I was very curious to ask one question. When we are migrating from natural materials to these man-made materials, for like these rubbers and other things. So what will be the long-term performance, sir, over the period of time? Because it has never been tested so far. And the same thing also holds good for, say, concrete, for example. So when I built my own house, we did some concrete cube test. 28 days, the strength was not achieved. But, using some fly ash, over a period of 56 days, the strength actually got maybe 70% more. So that seems to be very curious. What will be the long-term effect of these man-made materials compared to the natural materials? And there are a lot of research is going on in this front as well.
I agree with you that we need to see the long-term effects. The fly ash mixed concrete you pointed out. There has to, there can be some accelerated tests done in the laboratory, which can tell you that whether the life of the building is going to be 70 years or 50 years or 100 years, whatever. That will help. And of course, these rubber tire and other materials which are being researched, if we could have test tracks or some such this thing to see how the performance is, somebody has to come forward and be bold enough to implement it. Because right now I see what is written in the IS code, I can't go beyond that. So that becomes quite challenging to even measure up to what is not written in the IS code. How can we just test it and bring it, of course, into the codes if possible?
In fact, in one of the programs D.N. Singh had conducted in IIT Bombay, he called so many people to have some research ideas. I think I was also one. And this topic has been raised by some people there that we are depleting with the natural materials when the man-made materials is evolving things. So how we evaluate the long-term performance and how confidence we can implement those things in the application per se.
See, the whole problem comes that if uh, uh, these materials, somebody has to take that risk that even if it fails, they have to be ready to bear the cost and move forward. But till that happens, I think in our country we are into that fault finding mode, that whose fault it was, and there is no end to it.